You know, for centuries, we've basically had two names that define gravity for us: Isaac Newton and Albert Einstein. Their ideas are genius. They're why we can send probes to other planets. But what if there's a fundamental piece of the puzzle that's been overlooked? What if the key to a deeper, more unified theory of gravity isn't about more complexity, but about rethinking one of its most basic assumptions, especially when you factor in our expanding universe?
Okay, so here's our roadmap. First, we're going to tackle a huge cosmic mystery that's been bugging physicists for a long time. Then, we'll dive into rethinking a so-called universal constant. After that, we'll follow a clue hidden in a classic equation, take a tour of the evidence right here in our solar system, and finally, we'll ask the big question: are we looking at a brand new law of gravity?
All right, first things first. To really appreciate how cool this new idea is, we have to get a handle on the problem, the one that's been a real thorn in the side of physics for decades.
I mean, look at this journey. From the earliest ideas to Newton's laws and Einstein's relativity, our understanding of gravity has taken these incredible leaps forward. But here's the thing. Both Newton's and Einstein's theories work best in a sort of stable, almost static universe. They don't fully account for the constant forward march of time or the fact that the universe itself is expanding. And that creates what we can call the expanding universe gap, a major roadblock to a true theory of everything.
So, that's the big question, right? How do we bridge that gap? And what if the answer isn't some brand new, mind-bendingly complex theory? What if it's about looking at one of the most fundamental numbers in all of science and just flipping it on its head?
To get your head around this, let's try a little thought experiment. Imagine space-time is like a fluid, okay? A planet or a star isn't just sitting there. As it moves through time, it's acting like a magnetic stirrer in a beaker, creating this vortex around it. That vortex is its gravitational field, and it stands to reason that the strength of that vortex is directly connected to the properties of the object doing the stirring.
And that brings us to this absolutely game-changing question. We've always treated big G, the gravitational constant, as this magic number that's the same everywhere in the universe. We measure it, and then we plug it into our equations. But what if it's not a universal input at all? What if it's actually an output, a number that you can calculate directly from an object's own properties?
Now here's where it gets really cool. It's one thing to have a neat analogy, but how do you turn that into actual testable math? Well, it turns out the clue has been hiding in plain sight this whole time, inside one of the most famous equations in astrophysics.
So how do you build that bridge from a cool idea to something you can actually calculate? Well, it starts by taking a tool you've probably seen before, but just looking at it from a totally new angle.
And here it is, the good old escape velocity equation. This is the recipe that tells you how fast you gotta go to break free from a planet's gravitational pull. And the way we've always used it is, you plug in the planet's mass, its radius, and that universal constant, g, to figure out the velocity.
But watch this. With just a couple of simple moves from high school algebra, we can completely flip this thing around. First, you square both sides to get rid of that pesky square root. Then, you just shuffle the terms around to solve for g. And just like that, g is no longer a constant you have to assume. It's a value you can derive from things we can actually observe: an object's escape velocity, its radius, and its mass.
Okay, so that's the theory. It's elegant, it's simple, but does it actually hold up in the real world? I mean, if we use this new formula on the planets right here in our own cosmic backyard, do we get results that actually make sense? Let's start our tour with the inner solar system. Using publicly available data from NASA for each planet, we can calculate G. And the results? They're pretty incredible. For Mercury, Venus, Earth, and Mars, the numbers we get are ridiculously close, all hovering right around 6.6 times 10 to the negative 20.
All right, you might be thinking, sure, that works for the little rocky planets. But what about the giants, the absolute monsters of our solar system? These planets are unbelievably more massive. This should be the ultimate stress test. And yet, look at that. The derived G remains unbelievably stable, which just strengthens the case for this relationship.
And for the final test, the real nail-biter, we go all the way out to Pluto. It's tiny, it's icy, it's way out in the cosmic boonies. By all rights, it should be the exception, but the math, it just works. The calculated G is 6.48 times 10 to the negative 20, fitting right in with everybody else. It's perfect.
So when you put it all together on one chart,
From tiny, hot Mercury to icy, distant Pluto, the pattern is just, well, it's undeniable. Despite these massive differences in just about everything, size, composition, location, the value we get for G is consistently, beautifully clustered together. It's just, wow. And what this incredible consistency gives us is something totally new. An average for the gravitational constant that we didn't just measure in some lab on Earth. We derived it from the actual physical nature of the planets themselves. This gives us a whole new baseline for understanding how gravity works.
And this is where it all leads. What does all of this actually mean? What are the profound implications of being able to calculate G instead of just taking it as a given number that was handed down to us?
Well, it means we can actually rewrite the law of gravity itself. We start with Newton's classic formula, but now, instead of G, we substitute in the expression we just derived. And when you do that, something amazing happens. The mass and radius of the main planet and our new expression, they cancel out with terms in Newton's original formula. We're left with this much cleaner, much more direct equation where gravitational force is defined by escape velocity.
So, what's the bottom line here? Let's boil it down to 3 key takeaways. First, validation. This theory is verified by the data from our own solar system. Second, the constant. We now have a new derived average for G that's based on direct observation. And third, the future. And this is the big one. This points to a whole new way of doing physics, where we move from just assuming constants to actually deriving fundamental truths from the universe itself.
You know, this whole exploration just goes to show that sometimes the biggest breakthroughs don't come from discovering something exotic and new, but from looking at the laws we thought we knew inside and out and just seeing them in a completely different light. It really makes you wonder, doesn't it? What other universal truths are out there just waiting to be redefined?